record? Okay. All right, we should have people coming in. Here, they're starting to come in. All right, a little slow today. Hi, everyone. Welcome, welcome. Gonna just give it a moment, let everybody come on in. You can see it's flooding on in. All right, give me a moment. I'm gonna share my screen and we'll get started. Let me open up that. All right. Technology is a little slow today. Must be something in the air. All right, welcome everyone. For those of you that have never met me, I'm Lauren Traster. I'm the 4-H Teen and Leadership Program Coordinator here at UVM Extension, and I facilitate these teen science cafes. I'm going to pop into the chat right now. If anyone needs live captioning today, all you need to do is click on the link that I've just provided and that will get you to our live captioning. I see some of you know the drill already. Write your name and where you're from in our chat. So hi, Sage and KL, welcome back. Erin's here from Montpelier, welcome. Anna from Essex and Maddie from East Montpelier. Haley's joining us from Essex. Who else is here today? Because I know there is a lot more of you than what I'm seeing in the chat. Hi, Simon and Jack, welcome back. Awesome, Louis, all the way from New Mexico. Glad you could join us. Scout, hey Scout from Burlington, and Sterna's here, Southern Vermont. Cheyenne and Wayland from Braintree, and Kalani from Essex. Kyan, is it Kyan or Cian? I'm bad sometimes at how to pronounce some names, but I apologize for that, from Middlebury. I'm coming from Hyde Park, Vermont today. So keep introducing yourselves in the chat. We'd love to know who's here, where everyone's from. It's always just a nice way to just get a sense of the group that's here. So as you guys are continuing to introduce yourselves, I'm just going to go over the protocols we have when we hang out here in Zoom land. So you are all muted today, but that does not mean we don't want you to participate. There's 2 ways that you're going to be able to communicate, share your thoughts, ask questions, and chat back and forth with our presenter. We use the chat box and the Q&A box, and we use them very differently. So the chat box is where you're going to be responding back and forth to the presenter, because I know she's going to be asking you lots of questions. And you're going to share thoughts and ideas that you might have related to today's topic. But if you have questions for the presenter, you're going to put your question in the Q&A box, because we're going to get to everyone's question before the end of the day, but we might not get to your question right when you ask it. So it hangs out in the Q&A box until the presenter's ready to take your question. So just make sure that you're pretty specific about your question. Don't say, you know, how much is that? You know, that's just generic. Be specific about, you know, what slide, and give some context to what your question is about. That's going to help for us to be able to answer your questions. And in the Q&A box, you can click thumbs up, and that upvotes a question. That just lets us know more people are interested in a particular question. But again, we're going to answer all the questions today. So it doesn't matter if you're first on the list or last on the list, it will get answered. So we do ask that you just be courteous and respectful today and don't create any distractions. And because your only way of communication and the only way that you really could cause distractions is with the chat box, please make sure that you're using the chat box appropriately. Don't have random conversations and don't get all silly in the chat box. It really is meant to stay on topic. When you abuse the chat box, it does become quite disruptive to other people who are trying to focus and really follow the presenter and engage with the presenter. So we ask that you stay engaged, participate fully. I know today is going to just be a really interesting cafe. And before we get to today's topic, just want to remind you we have 3 different teen time programs that are going on right now or coming up in the near future. So I'll post this link in the chat once I'm done talking. And after today's program, you could go check them out. One is a conference in April. It's a national 4-H conference. So if you're someone who's really focused on issues and want to be able to make a difference, this conference, you get into roundtable discussions, and you actually create a presentation that you'll be presenting to people who work in Washington at the agencies that deal with those issues. The deadline, though, is today for that. So you'd have to kind of get on that real quick. We have one where we are doing some career exploration, and we have one more session next Wednesday. And we have the recording of the other 2 sessions. You do not have to have participated in the first 2 to come to next week. So check that out. And then we have a program coming up in the first weekend in March called Critical Conversations. We're having 4-H staff from Kentucky 4-H come and present a program that they run, which helps teens learn how to facilitate and understand these difficult conversations and topics of race and implicit bias and discrimination, and really learn how to have good conversations and move forward and understand these topics. So I'm really looking forward to that one, and hopefully you all might sign up for that. So moving on, I want to introduce our presenter today. We have Shelly Rayback, and she is going to be talking about secrets in the rings, what tree rings can tell us about our past, present, and future environments. So just a little bit about Shelly. She's a professor of geography and is also the director of the Environmental Sciences program, which sits in the College of Arts and Sciences at the University of Vermont. Her research interests focus on understanding how trees and shrubs record and respond to past climate and other environmental conditions. And her research takes place in locations like the Canadian Arctic, the Cascade Range, the Himalayas, and right here in New England. She has an undergraduate degree in English and French from Wellesley College and her PhD in geography from the University of British Columbia in Canada. So let's all welcome Shelly, and let's get ready to learn of what is hidden in those tree rings.
Okay, thank you. I'm going to go ahead and let's see, share my screen. Where did my PowerPoint go? And I'm going to hit the chat. So hopefully, and I'm just going to pull that over. Just give me 2 seconds. Let's see. Okay. Where's my, there we go. Sorry, come on, slideshow. There we go, from the beginning. All right, is that okay? Is the screen, I see the chat still up there. Should I?
Yeah, nope, you're good.
It's good, okay, so they can all see the picture and the PowerPoint. So hey everyone, thank you so much for coming this afternoon. I am just floored by your enthusiasm for coming to these teen science cafes, and I'm really excited to talk to you about something that I'm really interested in. And we'll take like the next 45 minutes. Hopefully I can whirl through a lot of these slides, and I'm totally open to answering your questions. So why don't we get started? So today we're going to talk about secrets in the rings, what tree rings can tell us about past, present, and the future of our planet. And I just wanted to start off with this beautiful picture of a swamp white oak. This is an oak that is found down in the Nature Conservancy's La Platte River, which is just down in South Burlington, Vermont. It was one of the sites that a bunch of my students and I went down to do some field work at. And it forms a nice background to this first quote by a couple colleagues of mine who are at the Swansea University in Wales. And they wrote in one of their papers, they wrote, "Trees are wonderful things," and I could not agree more. "They stand fixed in the landscape, often for centuries, taking carbon from the air and oxygen and hydrogen from the soil, water, and combine these components into layers of wood laid down in annual succession." So what they're talking about, the trees are basically undergoing photosynthesis, and through photosynthesis, they are able to create annual rings or tree rings in these trees. And that's really what I'm going to be talking a lot about today. But the first thing I wanted to ask all of you is, where do we find trees? It may seem like an obvious question, but I'm just curious, where do you think we find trees around the world? Just anywhere. You can tell me, maybe in the chat, type in some ideas where you think we can find trees. Okay, forest, great. Somebody wrote forest. Any particular maybe geographic locations like, I don't know, like Alaska or Vermont? Any place else?
I don't know if you saw, but Jack had written any suitable
Ooh,
climate.
any suitable climate? Oh, sorry. Okay. Outside. Okay, great. We find them outside. Yes, we find trees that where it's warm enough to grow. Okay. Okay, out in your yard, absolutely. Out here on the green of UVM, where we plant them in Montpelier, we have tree wells in the sidewalk. Great. So we have urban trees. So trees are really all over the place. They're, in the ground, they're in our yards, they're at our playgrounds, they're in our parks. Brazil, somebody said, inside. Yeah, some people have trees inside big pots. Lots of different places where we can find trees. Because I'm a geographer, I'm going to show you some maps. So this is a map of the planet, and it's showing you all over the world, different places. These are what we call biomes, places where certain kinds of vegetation grow. And so in many, many different locations around the world, we can find certain kinds of forests. We have places like down here around on the equator, this bright red color, the tropical rainforest. We also have places way far north, like right up close to where it starts to become more snow and ice in the Arctic. We have something called the boreal forest. Right here in New England, we have what is more of a mid-latitude deciduous forest. And even in places, I think I saw somebody who had joined us from New Mexico, down here in the southwestern United States, we actually have forests in our mountains as well. So there are a lot of different kinds of places where we find trees all over the world. And that makes my job easier because then I can go sample in lots of different places around the world and get information about these trees. So the next question I wanted to ask you was like, well, what makes a tree actually a tree? What kind of characteristics define a tree? And if you could just put into the chat anything that you might think of that would define what a tree is. How is a tree different from a shrub, for example? Okay, so somebody said it is making carbon. Okay, thank you, Simon. Yes, trees, they do photosynthesize. Yes, let's see. The trees are made out of wood, and they tend to be what we call woody species. Anything else? Okay, normally they're bigger and slower growing than shrubs. Correct. Definitely. There's definitely a height component there that helps to identify what a tree is. Any other thoughts? They have trunks. Good. And you know what? Usually trees have just one trunk. Sometimes they have two trunks, but normally to be classified as a tree, they have one trunk, or sometimes it's called a stem. Great. These are all wonderful suggestions. So what really does make a tree, you guys hit the nail right on the head. It's their growth form. They tend to be a single trunk. They tend to be woody. They tend to get pretty tall. To really be classified as a tree, they have to be at least 10 to 18 feet tall when they're mature. And they also have to be what we call perennial, meaning that they're alive, or they grow year after year after year. They don't die after one growing season or one summer. So, most trees, are alive after 2 years. Some trees are alive after many hundreds of years. So this is really what makes a tree a tree. Now, here's the question of the day. Have you ever looked at a stump of a tree? Okay, a tree that used to be there. Maybe somebody came along and cut it down with a chainsaw or an axe. And have you ever counted the rings? Yes, I see lots of people. Yes, yes, great. Excellent. Lots of people. I looked at the stump on the tree, but never counted the rings. Okay, so maybe next time you go back, Simon, you can count the rings if you ever see one. Okay, you know what? That makes you guys all, and I'll make kind of a funny pun for those who like puns. You are all sapling dendrochronologists, meaning you are people who have looked at tree rings. So that's what we're going to focus on today. We're going to focus on a field of science that's called dendrochronology, and a person who practices dendrochronology is called a dendrochronologist. And just the word dendrochronology, what do you think dendro means? Anybody have an idea? Okay, good guess. Ring. Okay, chrono, definitely. Chronology means some kind of recording or time series. Okay. Dendro, I'll put you out of your misery. Dendro comes from the Greek word dendron, meaning tree. And chronology is the science that actually deals with the assignment of dates and particular events to a tree ring. And more succinctly, we could say that it's the science of dating tree rings and studying the structure of those tree rings to really extract or get information out of those tree rings about the environment, about historical events, about processes that are going on outside in the world that the tree lives in. So what we're going to be talking about today is dendrochronology and the field of dendrochronology. So first, what I wanted to do is sort of talk a little bit about how trees grow, just to give us a little bit of background. Some of you may know from some of your biology classes that trees grow when cells begin to divide in something that's called the apical meristem. And the apical meristem can be found either at the very tip of either a small plant or even the tip of a tree. And they can also divide at the tips of roots. And so we have here over on the left-hand side, this is a microscopic picture of an apical meristem, and we've got cells that are dividing here, and then here's the root, and we see the dividing cells that happen here. So these are one way that trees can grow and get taller, or the roots can get longer. But the other way is through the division of cells that occur in something that's called the vascular cambium. And the cambium is located, if we were to sort of chop down a tree and look at the cross section of the stump, and if we were look at the very outside edge, really close to the bark, there's a layer of cells that begins to divide, and these cells divide, and they either form cells that are called the xylem, which are on the interior of this vascular cambium, or there are cells that form in the phloem, okay? And the phloem is on the outside, and that's directly next to the bark itself, okay? So this cambium is really, really important because these are the cells that allow basically the stem of the tree to get wider. Okay, these are the cells that get laid down and help to form a tree ring each year that the tree is growing. So here is just one of those cross sections. We've chopped down a tree and we've used some different kinds of sandpaper to make this cross section look really nice and clean, and you can see the rings kind of jumping out at you. You heard me mention this part that's called the xylem. This is here. This is the inside of the tree right through here, shown by these red brackets. And the xylem is really just sort of the support structure of the tree. This is part of the tree that we're going to talk about in a few minutes that dendrochronologists are really interested in. So this is this is the part of the tree that is formed on the inside of that vascular cambium. And then we have this really thin, and you can barely see it, but this little thin layer of cells that forms the phloem. And this becomes sort of part of the inner bark eventually. And this is really important because it transports the products of photosynthesis, okay? The sugars, for example, that happen that are created up in the leaves, and then they move down through the tree and they supply the tree with food. But dendrochronologists are really interested in this xylem part of the tree. But I just wanted you to be familiar sort of what we're looking at. When we look at this is sort of a model of how these cells form. This is as if we were looking at just one line of cells, and we've got the phloem cells. Those are the cells that transport the material from the leaves back down through the tree and redistribute them throughout the tree, okay? You'd have your vascular cambium sitting somewhere right about here. Those are the cells that divide. And when they divide and they create these first cells at the beginning of the summer, something that we call like the early part of the growing season during the summer here in the Northeast. And these cells are what we call our sort of early wood cells, okay, because they happen early in the summer. And these are laid down, they're created by the vascular cambium, and they produce one cell after the other as the summer begins to warm up, as trees have access to soil, water, the sunlight is coming through, temperatures are getting a little bit warmer, and they start to form this sort of first layer of cells. And as the summer goes on, they're going to have those early cells that were first formed in the early season. They tend to get a little bit bigger, and they have these big gaps in the middle called lumen in the center. And then we have a few more cells that get produced by the tree. And again, this is forming part of that xylem. This is part of that initial ring that's being laid down. And then finally, as we get towards the end of the growing season, the tree is beginning to shut down. It's produced everything that it needs to produce to put on more wood. And eventually this tree begins putting on what we call late wood over here, which is right up against the phloem. And that late wood tends to be a little bit darker in color, and it helps us to see and differentiate the different cells and then the tree rings themselves. So just give you this sort of gives you sort of an idea of how those cells are formed over the course of a summer, and they're laid down, and eventually what they form are one of these. So what we're looking at again is a photo under a microscope, and this happens to be of a tree called Eastern Hemlock. We have a lot of these here in Vermont, and we're looking at a ring that has been laid down by this Eastern Hemlock one year. And you can see that the cells are a little bit sort of lighter colored. These are the cells that have those big lumen in the center of them, and then they get a little bit darker as we go through the growing season. And then the end of the growing season, this is what we form the late wood cells. Okay, so it makes it really easy for us to tell that this is 1 year of annual growth. So this is, belongs to one growing season, one summer. The tree made that one particular ring. So this is what dendrochronologists are really interested in. We're interested in these tree rings. We're interested in what is sort of embedded or hidden within each of these rings, information that the tree essentially is kind of recording about its environment, about what the growing season was like for that particular tree in that 1 year. And the tree does this year after year after year. So every year, a tree is going to lay down one more ring, and that ring is going to have sort of secrets hidden within it that tell us something about what was happening to that tree in that particular year. So I want to let you know a little bit more about dendrochronology, that it's not just about counting tree rings, to figure out how old a tree is. That's what most of us do. That's why we like to go up to trees that have been cut down and we start to count the rings, and we're like, wow, this tree was, younger than I am, or this tree started to grow, 200 years before I was even born. That's really exciting. But dendrochronologists are also interested in all of that information that's embedded within those rings. But first, let's talk about some of the fun stuff before we even get to look at some of those tree rings. So first thing we have to do is we have to go out and do some field work, and dendrochronologists love to go out into the field. They love tromping around in the forest. This is probably one of their favorite things to do, and maybe one of the reasons why they go out and actually start being dendrochronologists in the first place, because they get to go see some really cool forests. This picture that you're seeing is a place called Granville Gulf. It's just south of Waitsville and Warren in the Green Mountains of Vermont, and you are looking at a picture of what we call an old growth Eastern Hemlock forest. And you can see here's a nice Eastern Hemlock tree here in the foreground. That's probably around maybe 250 to 300 years old. They're really old trees. And you can see one of my field assistants down here in the left-hand corner, that's Chris Hansen. And he comes out with me and helps me not get lost, so we can find the car again and we can get home. So a lot of dendrochronologists go out into forests all over the world, whether they're in places like Alaska, or they're in the Himalayas, or they're even here in New England, for example, in like Western Maine or in the White Mountains of New Hampshire. And so what we do is we go out to these forests and we sample the trees. And one of the ways that we sample them is we use this device here on the left-hand side. It has it has a handlebar, which is this blue thing, and then it has a drill bit that we actually twist by hand into the tree. There is a little drill at the tip of the bit that has grooves in it that when you begin to turn it, just like a screwdriver, it goes into the tree. And as it goes into the tree, it begins to cut basically a hole into the tree. And inside that hole is a pencil-shaped rod of wood that's coming from the tree itself. And here you can see what we've done is we are extracting this piece of wood. We're pulling it out with a very long, narrow spoon that we stick into the tree, and then we pull it out, and the tree core comes out. And you can actually see in this tree core, we've almost hit the center of the tree. You can see where the rings are curving right here. And then you can actually see the tree rings themselves. They're very quite evident. There, you can see them very easily, even with the naked eye. And then eventually, whoever you're working with, usually you do this in partners, they're going to help you put your tree core into a straw, and we label the straw, and then we take it back to the lab. And if you love power tools, you'll love Dendrochronology because we use a lot of power tools. So the first thing we do is we take the cores out of the straws and we mount them. We mount them in these wooden mounts that you see here. We glue them down just with Elmer's glue. We let them dry, and then we have to sand them. So what you see here is a belt sander that we flipped upside down. We turn it on, and the belt is running a piece of sandpaper very quickly, and we just flip the cores over and we push them down on the sanding belt, and it sands it for us, and it makes a really nice flat surface. This other piece down here that was picture was taken by my colleague Paula Murakami, who works for U.S. Forest Service. This is from sugar maple. So some people will actually go out and they'll take a chainsaw and they'll cut down a tree and then sand it as well. And then this is what we look at. And we look at our cores or our cross sections of trees under a pretty fancy microscope like you see here. And we've got some interesting lights. These are our gooseneck lights that illuminate what we're looking at underneath the microscope. And then we do measuring, and we can either do measuring on this machine that this core is sitting on top of. It's called a measuring table. And some people will actually measure on a computer screen, and you can measure the width of each of these individual tree rings. And this is a picture just directly under the microscope where we would be measuring the distance from one edge of this late wood, that dark band, to the next edge, and that would be 1 year's worth of growth. And so this is what we're interested in. And we would measure hundreds and hundreds of rings, even in just one tree, and then we would measure rings and cores from multiple trees, and we begin to get an idea of how trees grow in a particular forest over long periods of time by measuring these particular rings. We have to do something in addition to, doing the measuring. We do something that's called cross-dating. And cross-dating is a pretty long and drawn out procedure, but sort of basically to make it more simple, cross-dating is a process where we match patterns in ring widths within a tree, between trees, and across multiple trees. And then we use it to make sure that we correctly date each of those tree rings. We assign what we call a calendar year. So I might be able to say that a particular tree, maybe we cored it in 2020, like this past summer. And what I'll be able to do is assign a calendar date to each one of those rings as we go backwards in time. So the next ring would be 2019, and the next ring would be 2018, and so on and so on and so on, until we get to the center of the tree. And maybe the tree started growing in 1900, or maybe it started growing in 1650. So this whole process of cross-dating is really tedious. So if you like doing tedious things like puzzles with 1,000 pieces, you would be great at cross dating. I once had an undergraduate assistant in the lab who liked to build models, inside those bottles, and he was a great technician in the lab because he just could do lots of really small, detailed things, and he really enjoyed sort of this cross dating process. So, anyways, it helps us to date our tree rings, and it helps us to develop what we call a chronology. So that's just a series of measurements of tree ring widths, and it's done, we get these series that for long periods of time. So we know how the tree grew for maybe 200 years for each of those annual increments, each of those tree rings. All right, so let me ask you another question. How old are the oldest living trees in the world? How old do you think they are? Maybe some of you might know. Some of you might know what that tree is on the right-hand side as well. Any guesses? All right, well, I don't know if I can see how many zeros those are from Jack, but that's a really old tree. Ooh, okay. Shretna says 2,000 years. Somebody, let's see, Alice says thousands of years. Okay. 4,800. Did you skip ahead in my slides? Okay, that's a really good guess, Erin. Thank you. So one of the trees that we're looking here on the left-hand side is something that's called a bristlecone pine. These are some of the oldest trees in the world. And here we're looking at one of the bristlecone pine stands that is in a place in California. These trees are 5,000 years old, and they're still alive. These are amazing specimens of trees. These are trees that have been alive for 5,000 years and are still alive today. And so these are amazing organisms that live on the surface of the earth. And many dendrochronologists have actually cored these trees to try to understand different kinds of things about these trees. Maybe their past climate that these trees lived in, or maybe how much rain fell over the last 5,000 years. So there's a lot of different questions that we can ask. But the good thing is if we can have these long chronologies, particularly from live trees, we can go back in time, whether it's only a few hundred years, like here in Vermont, or maybe a few thousand years, like in California, or in places like the Inner Basin area in Nevada, where we find bristlecone pines. And if we're lucky, sometimes we can find pieces of wood that come from other places, like historical buildings, or maybe we dig up old stumps on the sides of rivers when the rivers wash away some of the riverbanks. And we can take these trees, these old timbers from historical buildings or old logs, and we can add them into our chronologies to actually make them go back longer in time. And so we can sometimes get chronologies that go back 400 years, 500 years, maybe 1,000 years. And when we're really lucky, some kinds of species like bristlecone pines can let us go back 5,000 years. Okay, so somebody asked if that was a redwood. No, redwoods are actually a different tree species, and they grow typically in Northern California. The bristlecone pines grow in Southern California, where it's even harder to grow because it's so dry in many of those regions. I'm going to talk about just a minute. Somebody asked, can you figure out how the climate has changed from bristlecone pines? Well, I'll just talk about that in just a second. You're right there with me. Okay, so what can tree rings tell us? Okay, we know that we can count them. We figure out the age of a tree. We've talked a little bit about how you do field work and how you do lab work. Now let's talk about what tree rings can actually tell us. And I think they can tell us really, really cool stuff. They can, first of all, allow us to look backwards in time. Okay, so I've already talked about that, backwards in time for 100 years, 1,000 years. And this is really important because a lot of times we don't have records that people have written down over the last 100 years or the last 1,000 years telling us about what our environment has been like in the past. It's really actually only been in the last 100 years, maybe 110 years, actually, for most of the United States and Canada, when we actually have written records. So trees are this really cool thing that we call part of the proxy data that allows us to look backwards in time. The trees actually substitute for written records, and I'll explain that in just a second. They're also really cool because they let us see changes from one year to the next, because each of those tree rings is 1 year of growth. And each of those tree rings records information about the tree's environment. It could record information about temperature, record information about moisture, could record whether there's been a fire there or whether the tree had been attacked by insects. Trees are like huge archives. They take in all that information and they store it in the physical record of that tree ring. And it's kind of like a permanent record. As long as the tree is there on the landscape, we can look at that information, extract that information, and we can find out about what happened in the past. And the questions that tree ring chronologies can help us understand about the past were things like, what was past climate like? So that was a good sort of question. How has our environment changed? And it can also help us see if the changes that we're seeing in our environment today are unusual or strange or something to be alarmed about. So these are really, really excellent records to look at the past and compare what the current situation is with the past and say, oh, wow, that never happened before. Okay, so the first thing that I want to talk about here a little bit is how we can use tree rings to understand past climate. Okay, and I have to kind of bring you up to speed on maybe how we do this. So let's pretend that we're going to go out to Mount Mansfield. Mount Mansfield is the tallest mountain in Vermont. For those of you who are not from Vermont, it's this nice mountain here. Oops, let's say there's my cursor. It's this nice mountain here. And maybe some of you know that might be familiar with Mount Mansfield because we're Stowe ski resort is on the other side of it. And let's say we decide that we're going to go sample some trees there, some red spruce that we see here on the right-hand side picture. And we're going to go to Mount Mansfield. We're going to sample a bunch of red spruce trees with our increment borer with the blue handle. We're going to go back to the lab and we're going to clean up our cores and we're going to sand them. We're going to mount them. We're going to look at them under a microscope. And so we might see a core that looks like something like this. This is actually a red spruce core. And now what we're going to do is, after we've done all our measuring, we're going to compare all of those measurements for each year to some what we call climate data. And climate data are collected at meteorological stations. There's one at the Burlington Airport, if any of you have ever been there. Lots of airports have National Weather Service climate stations located there, and they've been collecting data for sometimes or sometimes at least 100 years. I think in Burlington we have about 120 years worth of data. So what we're going to do is we're going to look at the data that we collected for our tree ringlets, and we're going to compare it with the data that we collected for climate in the general region that we live in. So maybe we're going to look at temperature data, and maybe we're interested in summer temperature data. And so what we're going to do is we're going to take a look at these tree rings, and we're going to try to figure out the relationship between the width of the tree ring and how warm or how cool it is. And so you might expect, for example, that a wide tree ring might form when a tree has all the sunlight, it's a nice warm summer, and it's able to photosynthesize. It's not stressed. And so it's able to photosynthesize, it's able to create cells, and it's able to lay down a nice layer of wood in that year's tree ring. So this big fat tree ring here, we're going to say that that is a tree ring that represents very warm temperatures. Now, we might have a cool year. Maybe it wasn't such a great summer. Maybe it was kind of cool and rainy and we didn't get as much sunlight and it wasn't as warm. And so maybe we form a ring that is quite narrow. Okay. And sometimes, yes, somebody asked it, or somebody mentioned that it would depend on the tree. Absolutely. Every tree is different. Every tree is going to respond slightly differently to their environmental conditions. But overall, when we look at like a stand or forest stand, a bunch of trees sitting there together, they're all going to respond pretty much the same way to temperature, or maybe to precipitation, rainfall in that particular location. So once we have this idea that we have this kind of signal that trees are going to form wide rings when it's warm in the summer and maybe slightly more narrow rings when it's cooler, what we're describing basically is a relationship between two what we call variables, the variable of tree ring width and the variable of temperature. And maybe some of you have, if you're in high school, maybe you've taken a statistics class, and you might be familiar with the word a correlation. And a correlation is a relationship. It describes a relationship between two variables. So when ring width goes up and temperature goes up, that's a positive relationship. When ring widths go down and temperature goes down, that's also a positive relationship. If we have temperatures going up and ring widths going down, that's a negative relationship, okay? So once we figure out and we sort of establish this relationship, this is a representation of this. This is just sort of showing us tree rings, which are represented each year by this blue line. And every time you sort of see a little inflection point, that's a measurement, okay? And they're connected. And then we see temperature, and it's following along. So we see a pretty good relationship. When the ring widths go up, temperature goes up. When temperature goes down, the ring widths go down and they're more narrow. So we're sort of establishing this sort of correlative relationship between these two different variables. And once we have that relationship, okay, and I'm going to show you this, we're going to focus here on the right-hand side of the diagram, okay? So what we are doing is we're putting together our tree ring widths that we have and our climate data that somebody has collected at the National Weather Service. And these are two data sets that one are tree rings, and then the temperature data set's what we call our observed data set. It means that somebody has actually been there to observe this data, has looked at a thermometer day after day, year after year, and recorded the temperatures, okay? So we're comparing those two data sets, and we do something that we call calibrating. We're establishing a relationship between the tree ring widths and the temperature, okay? Then let's say our climate data stops in 1900. Nobody was around to record it. So what we have to do is we're going to have to estimate backwards in time what temperatures might have been. But the only piece of data that we have in this relationship that goes back that far are our tree ring data. So what we're using is we're using the tree ring data that was that's before 1900 to tell us something about temperature. It's establishing a relationship prior to 1900 with our observational data. We understand that wide rings equal warm temperatures, narrow rings equal narrow temperatures. So if we look at data prior, tree ring data prior to 1900, we can say, wide rings are going to represent warmer temperatures. Okay, and so how do we know that these statistical shenanigans actually work? Okay, so I'm going to give you sort of a proof of concept, if you will. So first of all, does anybody know what happens to temperature when a volcano erupts? This is Mount Pinatubo in the Philippines, and this is one, this erupted in 1991 and gave us a lot of information about what happens to temperature when a volcano erupts. Anybody have a guess? Somebody said it goes up. Somebody says it gets cooler. Okay, actually, so I think Lewis, you're correct, because it does, and Aaron as well, it does get cooler because soot is in the air. Thank you, Aaron. In fact, that's exactly what happens when a volcano has an explosive, yes, eruption, like when Mount Tambora erupted in Indonesia in 1815. It was an eruption that spewed an enormous amount of ash into the atmosphere. And what happens is that ash reflects incoming sunlight, and that sunlight gets reflected back out into outer space, and it never makes it to the surface of the earth to warm the earth's surface. So somebody mentioned a year without a summer. Yes, absolutely. So the year following the eruption on Mount Tambora in 1815, 1816 is considered a year without a summer in places like New England and Europe, where temperatures plummeted, and it actually snowed in New England in July of 1816 because it was so cold. A lot of crops were ruined in that summer, and a lot of people actually left New England after 1816 because of that event. So what I want to show you here is looking at the year, actually 1816, and this, we've taken data and we've created a map. This is based on lots and lots of different tree ring chronologies from all around the world. And what this is actually showing you is for that 1 year after the eruption of Mount Tambora, that temperatures actually dropped. And this was being reconstructed from the tree rings themselves. And anywhere you see those purple or blue colors, like they show down here in this, legend down here, these are areas where temperature was a lot cooler, up to 2 degrees Celsius cooler than what was normal. So we can see large areas of Europe were much cooler. We can see large parts of the eastern United States were also much cooler. So hopefully this gives you a little bit of an understanding, that this actually does work. And I just wanted to show you this. I just picked out a whole bunch of other dates. Just to sort of show you sort of snapshots in time where different dendrochronologists, this was a dendrochronologist, a guy named Keith Britha, who did this and created hundreds of these yearly snapshots of what temperature was like in the Northern Hemisphere using tree ring data. And I just picked out 16, 17, 76, and then 1776 and 1876, just to kind of give you an idea of what the tree rings can tell us about temperature in those particular years. I also wanted to just show you, here is what we call a time series down here below. And this is showing temperature trends that were based on tree ring reconstructions for the entire Northern Hemisphere. And anywhere that you see in red are showing years or periods of time that were extremely warm. Anytime you see a dip down into the blue, these were time periods where temperatures across the Northern Hemisphere were much cooler. So anyways, I just wanted to kind of show that to you. All right, I wanted to shift gears and talk a little bit about how trees can be used to understand past climate in different ways. Can any of you think of some periods in US history that have been particularly dry? Ah, the Dust Bowl. Okay, Ezra, thank you. I'm not familiar with Black Sunday. Can you clarify? I'm not sure what that means. You don't have to if you don't want to. But the Dust Bowl is an excellent one. That was one that comes to my mind very quickly. There are actually a lot of very dry periods in the United States in particular. We talk about these dry periods and refer to them as what we call drought. And drought is just a really long period of time when a particular region receives a lot less rainfall than it normally does. True. Good suggestion. Good, Aaron. You said that not all of the U.S. right now, but we are in a drought in Vermont. Excellent. So that's a good comment there. And Black Sunday was a part of the Dust Bowl, the culmination of it. Oh, okay. I've not heard that term. I'll have to look that up. Thank you for alerting me to that. So there are a lot of different time periods in US history, even just within the 20th century and into the 21st century, where parts of the United States have experienced drought. We have the Dust Bowl in the 1930s. There was a very long period of drought in Texas and the Southwest in the 1950s. And then we have had other periods of episodic drought in the Western US in the 1980s, the 2000-2002 drought in Colorado, and more recently, a drought that happened in California. And of course now, as a reference to Vermont being in a dry period as well. So some of you may have heard on maybe the news over the last few years that California was going through an exceptional drought period. So droughts are something that are familiar to a lot of people, a lot of Americans, particularly people who live in the Western United States. And California is just one of the most recent episodes of drought that has occurred that has been quite severe. And you can see on the map, which shows sort of a period of time from 2011 to 2015, how California became progressively drier over this period until much of the state was in what we call exceptional drought conditions by 2015. So when we look at tree rings, we can also not only determine past temperatures, but we can also see when droughts occurred and oftentimes how bad those droughts are, how long they lasted. And if we look at them over a long period of time, we can actually see if drought is sort of like a normal condition for a particular region. And so oftentimes we're looking for those series of very narrow rings like we see over here on the right-hand portion of this image. And it's just because photosynthesis has slown down and is not able to lay down as many cells in a particular summer when water is at a premium. So maybe some of you have heard about historically in the U.S. Something called the Lost Colony of Roanoke and Jamestown. These were two of initial settlements along the eastern coast of the United States when the U.S. was being settled by Europeans, and we can use tree rings have been used very effectively to be able to understand past periods of drought and possibly their effect on the success or failure of different societies. And a group of dendrochronologists in the end of the 1990s looked at an area around Virginia, along the coast, North Carolina, and we're trying to understand whether drought was a factor in the failure, really, of the Jamestown and the Roanoke colonies. And so what they did was they went and sampled these bald cypress trees, which are trees that tend to grow to be very, very old, sometimes 800 years old, in areas like Southern Virginia. And what they were trying to look at was look at the tree ring wicks to see if there was evidence of drought in this particular area. And what they were able to do is they were able to develop an 800-year chronology, and they were able to relate it with climate data from the 20th century that was information about moisture availability and precipitation. We use something that's called the Palmer Hydrological Drought Index, which you see over here. This is just a measure of moisture availability. And this particular diagram that we see here, again, this is a time series of measurements of tree ring widths. And what we're seeing is that if the line drops below this 0 line here, these are periods when the area was experiencing very, very dry conditions. And then any lines that you see popping up over here at different time periods, these are when this region tended to experience much wetter conditions. And so they have this chronology that they created that goes back to 1118, so an 800-year chronology. And what they were able to discover is that they looked at two different time periods when the lost colony of Roanoke was established, and they also looked at when the Jamestown colony was established. And what they were able to figure out was when the lost colony was established it was the driest 3 years in an 800-year period. That these poor people decided to establish their colony during a period of time where there was basically very little rainfall for them to grow their crops. The rivers had dried up, and basically that colony disappeared, and that may have been one of the reasons that that colony failed, because of those extreme dry conditions. They also found extreme dry conditions during the period of time that the Jamestown colony was settled. For a period between 1606 and 1612 were some of the worst years of drought. And this was a time period when I think it was something like about 1,600 people died within the colony because of starvation and because of poor water quality in that particular area. So this was a dendrochronologist's contribution to trying to understand sort of what historically had happened to those colonies by identifying that drought was a really important factor in the demise of the lost colony of Roanoke, but also in the really rough time that the Jamestown colony experienced while it was settling. So not only can tree rings tell us about sort of historical context, but they can also help us to understand really past drought in a or more recent drought in a longer term context. So I'm going to turn back to the California drought, and we have a picture on the upper right hand corner. It's a satellite picture from the satellite MODIS that was taken in 2015, and what it's showing you is snow in the Sierra Nevada mountains. And really what I want to emphasize with this picture is that there actually isn't a lot of snow. Usually the Sierra Nevadas are covered in snow, 6 feet deep snowpack pretty much all winter long. And then eventually that snow melts and it runs into rivers, and it helps the people of California to water their agricultural fields. It's a source of water for drinking, for swimming pools, for municipal water use, the water that comes out of your tap if you live in a place like California. Unfortunately, as I mentioned, California went through a really, really bad drought, really that was at its peak in about 2015. And a friend of mine, her name's Sumaya Belmasheri, she decided to look at trees that were growing in California, a species called blue oak. And she was able to go backwards in time with her reconstruction. And her reconstruction goes back, I think, about 500 years here. And she was able to discover that the 2015 drought was the worst drought that California had experienced in over 500 years. So this was a huge wake-up call to California and also other people who live in the Western United States, where water is very scarce, oftentimes. And to see that 2015 was really the worst year for drought on a very long, over a very long time period was quite scary for the people in California and the people out west, principally because our climate has been changing recently over the 20th century, where we're seeing higher temperatures and less precipitation because of climate change. And so this is a sort of a wake-up call, in a sense, for California to see that, wow, we really are seeing pretty bad conditions that are occurring in California, most recently in this drought. And are we going to see similar drought conditions with rising temperatures and declining precipitation in California in the future? So yes, somebody has just said that reminds them of what's going on in Bolivia. Yeah, drought is, conditions are happening all over the world, in places like, for example, Australia, that is also undergoing drought conditions periodically, and those drought conditions are worsening and causing many problems for people who live in those areas. Just focusing here, of a shout out to our person who's joined us from New Mexico. Drought is a very big topic in the Western United States, and I just wanted to show this area to you. This is part of the Southwestern United States, and it's an area that relies for much of its water source from the rivers that come out of places like Colorado, like the Colorado River, that snakes down here out of the Rocky Mountains. It gets its water from the snowpack that melts and drains into these rivers, the Green River, and then these rivers flow through states like Utah and Arizona, and then through California, and then out into the Pacific Ocean. And many of these states in this area rely upon this water source coming out of these rivers, coming out of the high mountains here in the central portion of the southwestern United States. So much so that back in 1922, a group of these states got together and decided to create basically the Colorado River Pact, where they would share the water that comes out of this river across all of these states, and is a source of water for different towns and cities. It's a source of water for agriculture production out in these areas. Now, the problem is that when they made this decision back in 1922, there was a lot of water flowing through the Colorado River. And so when they did the allocation, they were making their decision based on a time period of probably, I don't know, 2 or 3 decades where there seemed to be a lot of water in the Colorado. Unfortunately, as we've moved towards the present day, sorry, this is the Colorado River Compact between these among these 7 states, and they redistributed the water rights to each of these states. as we moved into the present, what began to happen was that we began to see a lot more variability in the amount of water that was flowing through the Colorado River. And so some years there was a lot of water, like some of these years here in the early 1980s, but in other years there wasn't a lot of water at all. And all of a sudden these states are having to share not a lot of water. And this is becoming more of the norm these years when we don't have a lot of water. So dendrochronologists have been called in to try to help people who are managing those water supplies understand what the conditions may be like in the future as our temperatures continue to increase and as water becomes a more scarce resource. And so one of my colleagues, a woman named Connie Woodhouse, who works at University of Arizona, has done an incredible amount of research about this. She has looked at tree rings from lots of different trees all around the southwestern United States. And what she has been able to do is actually reconstruct precipitation or moisture or even stream flow through these rivers, because trees respond to water the same way, similarly to water, just sort of the amount of water that moves through these rivers. And so she's looked at rivers like the Colorado River that goes through the southwestern United States, the Sacramento River that is in sort of central California, and she's been able to reconstruct using tree rings how much water was flowing through those rivers over long periods of time, back, to 800 AD up until pretty much the present. And what she was able to identify was a period of time that you can see sort of in this light tan area where we had very warm temperatures, very low amounts of precipitation, and we get these very long, intense droughts. And so what Dr. Woodhouse was trying to do was to say, hey, as we move into the future, we may have a situation where we do have high temperatures and low amounts of water, very similar to this drought that happened back in the mid 12th century. And we may not have enough water for the entire sort of Southwest to be able to share. So again, this is sort of an idea that we need to pay attention to our water supply in the future, and tree rings have helped us to see that. Okay, so I'm going to move into the last piece. I hope you guys can stay with me for a little bit. Can anybody name maybe one of the most important natural disasters that's happening in the Western United States is right now? Hurricanes, good suggestion, but hurricanes happen wildfires. Yes, excellent, everybody. Great. Wildfires is becoming one of the largest and most expensive natural disasters that are happening in the Western US. If you've been watching TV, you may have seen that this past summer, where good portions of California, Oregon, and Washington were on fire this past summer. And so this is becoming a bigger and bigger problem out in the Western United States. Dendrochronologists are interested in fire. They're interested in disturbances that affect trees. And fire is one of those disturbances that impacts trees. And trees actually record fire that occurs in the areas that they are growing. That type of dendrochronology is something we call dendropyrochronology, pyro meaning for fire. And dendrochronologists, instead of looking just at the individual tree rings, they actually try to date the tree scars that are left by fire that has burned at the base of a tree. And we use this to understand how many times maybe fire has occurred at a particular site, and maybe what that fire is doing to that particular forest or ecosystem. So people who do dendropyrochronology use a couple different kinds of tools to be able to do this. Principally is that they use a chainsaw, and this is my colleague Jim Spear. He's cutting into a tree that has a tree scar. So we go into areas where we find trees that have been burned, but they haven't been completely destroyed. And oftentimes a fire will burn at the base of the tree, and it'll just scar the tree enough that it creates what we call these cat face scars. I know they actually look like a cat ear, and I'm not exactly sure why it's called a cat face, but it's a burn burn at the base of the tree. And it's these burns that we look at. And we use these burns. Let's see if I can show you a picture. This is a cross section of a tree that has been sanded and then dated. And the person has identified when these scars occur. And sometimes if a tree has been burned repeatedly, the tree will actually repair itself, and it'll close over that wound, and that wound stays embedded within the tree itself. So we oftentimes can see the evidence of multiple scars inside a tree. And if we chop it down and then we sand it and we look at it under the microscope, we can date when those scars occurred. Now, fire in the southwestern United States has been one of the foci of many dendrochronologists, particularly in forests like ponderosa pine that we find in places like New Mexico and California, Oregon, and Arizona. This is a kind of tree that tends to grow in forests that actually like fire. They need fire to survive. Here's a map that just shows you some of the locations of where you find ponderosa pine. So what has happened in the past is that these forests, like ponderosa pine forests, grow when smaller trees begin to grow in the understory. Sometimes they're ponderosa pine, but other times they're other trees. And normally what would happen is we'd have these small fires that would come through, small surface fires. And the small surface fires would burn up the stuff in the understory and would allow the bigger trees to continue to grow. And so we ended up with these fires that opened up the trees or opened up the understory and created these very sort of open forest like we saw in the previous image. And so that was sort of what the normal pattern was. And dendrochronologists who look at fire scars would look at their cross sections like we see here, and we see multiple small fires that had probably gone through this particular forest where this tree was sampled multiple times over the lifetime of that tree. And dendrochronologists have been collecting their samples all over the western United States here in many different many different states. And over time, they have created these fire scar chronologies where they have gone to certain mountain ranges like the Black Hills or the Front Range or the Jimenez Mountains, and they create chronologies for each of the sites, and each of these triangles represents a fire scar that has been identified. And what they noticed is that in the southwestern United States that they had lots of fires, and there tended to be a lot of fires in certain mountain ranges. Sometimes the fire scars lined up between the different mountain ranges, so we begin to see patterns across multiple mountain ranges. But then the other thing that they saw was that fires seemed to disappear once we got into the 20th century. And they started to kind of scratch their heads and be like, well, why did this happen? Why did these fires all of a sudden disappear? And at the same time, they began to see something happening to their forests, where their forests began to fill in again with these smaller trees, and then their forests became really dense. And we started to see forests that used to be open like this become forests that had lots of understory trees growing in that eventually became very dense and sometimes are what we call dog hair thickets. And these forests became very sort of what we call overstocked, or they very cluttered because these fires weren't burning in these forests and sort of cleaning out the understory so that the bigger trees could continue to grow. And so scientists, dendrochronologists were instrumental in this, in really beginning to piece together the history of the Southwest. And they began to realize that things that humans had done had eliminated fire from these forest ecosystems. And so some of the things they did were they ran cattle and sheep through many of these mountain areas, and the cattle and sheep ate up a lot of the grasses and the herbs and forbs that would have helped to carry fire through a forest and would have helped to burn the understory. We also had things like trains that were and railroads that were built through areas, and sometimes the railroads would clear really big swaths of forest, so forest fires couldn't kind of continually burn across the landscape. So they might burn one area, but they wouldn't burn another. And then the other thing that really happened was that the U.S. Forest Service made a decision that basically fire was bad and that they needed to suppress all fires that were burning in the forests in the southwestern United States and in other places. And so the forest fires never burned up that smaller stuff that was in the understory. And so what we began to see as we moved into the 20th and 21st century are these really big fires, these catastrophic fires, or sometimes they're now being called megafires. And these fires are what we saw this past summer in places like California and Oregon and Washington, where they're totally uncontrollable and they actually burn an entire forest to the ground instead of just cleaning out that understory. So we have this history that we know that our actions in the Western United States have created these conditions, but we also have climate change, again, that are creating really bad conditions for this forest. We know that temperatures are increasing in many parts of the country, and you can see on the map the temperature change that has occurred since about 1895. Any of these really red areas, purple areas, are areas where temperatures have increased by at least 3 degrees Celsius in some of these areas. So it's getting really hot. We are also figuring out that wildfire frequency is beginning to happen more and more often. And so as we get further towards the present, we're seeing more and more wildfires. We think that this is because of increasing temperatures. We think that it's also because the snow pack is melting out earlier in the spring, and so it creates conditions throughout the summer that are much drier, that normally would have been moist by snow melting very, very slowly. And the number of days per year is actually lengthening. The fire seasons are actually lengthening. So we're getting sort of the wider portions of this diagram is showing us areas where the fire season is even longer. So we're getting situations that look like this, where fire has come into our cities and towns. It's forcing evacuation. It's forcing massive efforts and money spent to control these wildfires. And I guess I just want to emphasize that it's dendrochronologists that have helped us to understand these patterns of wildfires in the Western United States. Okay, so I'm going to sort of end there just to give you an introduction to what dendrochronology can tell us a little bit about in terms of past climate. This is just a picture of me on top of Mount Moosilauke in New Hampshire, and also one of my favorite spots in Vermont. If any of you are looking to find old growth forests, this is a terrific spot. You go up the Abbey Pond Trail and you'll see old growth eastern hemlock that are at least 300 to 400 years old. So if you like old trees like I do, this is a good spot to go to. Okay, so I'm happy to answer any questions that you might have, and
Yes.
thank you for your patience.
That was fantastic. Thank you. So before we get to the questions that are in the Q&A box, I'm going to launch a poll right now. If you all can just quickly take this, we'd like to know at every cafe what you thought of it. And then the second part of the question is, did you learn something? So rating 1 to 5, 5 obviously being, yeah, you like the cafe, and yes, you learned a lot. 1 is no. But my Lord, that was so fascinating. I hope you all got as much out of it as I did. So, yeah, you can't see the results because I haven't shared them yet, Jack or Simon. So if you can see it to take the poll, if not, just put your response in the chat. So we're just going to give it another 30 seconds and then we'll go to the question. If you haven't put a question in the Q&A, go ahead. We are probably going to run just a little over time, but hopefully we can get all the questions answered and not keep you too late. All right, so I'm going to close the poll right now. Thank you all for that. And let's go in and answer some of these questions. So Erin asks, are there a lot of younger bristlecone pines, or do we only see mostly older ones now?
Good question. There are some young bristlecone pines, but here I'll just be upfront and honest. I don't work with bristlecone pines, so I don't see them very often. Most of my attention is usually looking at the really, really older ones. But yes, there are some. They grow very, very, very slowly because there's not much water, and it tends to be very, very, very dry in those locations.
I have done some tree sampling before, and this question always gets asked. When you extract that piece of wood from the tree for sampling, do you cover up the hole made in the tree, and could it harm the tree?
Okay, that's a great question. I always get answered that or asked that. I don't cover up the hole. Most of the time I am coring conifer trees, so trees that have needles, and trees do a really good job of protecting themselves when they are injured. They will immediately begin to deal with the hole by putting sap into it. And I have gone back to sites where I have sampled before, and I can't find the holes where I sampled before. So I think trees are really good at protecting themselves. So yes, I would say for the most part, trees are, it's okay. They're able to rebound from that. There's a lot more damage done by woodpeckers, I think, from a lot of trees.
So two questions that I think are a little bit related, so I'm going to ask them together. One is, how do you see years when the trees got too much water? And then how do you know if the ring size is smaller because it is too hot or if it's because it's too cold?
Good question. Yeah, okay. So a lot of that is so it goes back to some of the statistical shenanigans we do. It has to do with identifying the one climate variable, the one either temperature or precipitation that is most strongly related to the ring widths. Lots of different environmental factors affect trees, absolutely. As dendrochronologists, we try to zero in on usually the one climate factor that we're interested in. So for some tree species like eastern hemlock, for example, like in the picture here, those trees are super sensitive to precipitation. Other tree species, maybe like spruce and fir that you might find in the far north in the boreal forest, those trees are really super sensitive to temperature. So it kind of depends on the location, it depends on the tree species. And when we do those correlations, when we're looking at the relationship between the tree ring width and the climate, temperature or precipitation, whatever you're looking at, we're looking for the strongest correlation, and that's the one that we go after. I hope that helps explain that.
Great. So Cheyenne asks, you talk a lot about looking at the past with tree rings.
Yeah.
Can you predict the future?
That's a good question. There are scientists who look at relationships with using tree rings and climate data, and they say, okay, this is how the tree has responded in the 20th century or in the early part of the 21st century. And we can use what are called climate models that go into the future to try to predict what future climate might be like. And so, I have not seen people actually predict what tree growth might be like on a year-to-year basis, but there is some studies that are trying to predict on sort of a larger scale how trees might grow, if they might be growing really well because they're getting, for example, more water, or they might be growing better because they're getting more carbon dioxide. But I haven't seen specifically using tree rings to predict into the future.
Great. And I'm going to ask no more questions coming in at this point. We'll answer the final 3 questions, all from Erin, by the way, who I think, Erin, you might have a future as a dendrochronologist because you have some good questions here.
Yeah.
So the first she asked is, have you ever tried to sample a tree and found that the core was rotten? How much history do you think is lost because of things like this?
Good. Yeah, good question. Yes, all the time. Tons and tons of trees you sample and they are already rotten in the center. And it's very frustrating. So a lot of times what we do is we go back, like we'll pull the core out and we'll see that it's all rotten and it falls on the ground, and we'll take another sample and see if we can find get a better core. Yeah, sometimes rings are lost and history is lost and there's not much we can do about it. It's unfortunate, and that's why For example, I'm doing a project right now where I'm teaming up with some people who sampled trees back in the 1970s, and they have agreed to lend me their cores. And so they have cores from trees that are a lot older than the trees that I can find now. And so I can put my cores together with their cores, and we can get even longer chronologies, because those trees are no longer alive on the landscape, or those trees, the interiors of them are already rotten.
Nice. When looking at one variable like temperature, how do
Mhm.
you control or account for other variables?
You don't. That's a good question. That is part of something that we call explained variability. So sometimes we might be able to say that, for example, July temperature tells us a lot about how that tree is growing. And we might say that that's the dominant climate factor. And maybe we say that it explains 75% of the growth of that tree. We still have 25% that we may not know what it is. Maybe it's precipitation, maybe it's just that individual tree is its own genetic individual, maybe it got attacked by insects one particular year. I mean, there is always information that we don't know, and that probably we'll never know if we don't have if we're just sampling trees out in the natural environment and they're not in a greenhouse. Some of it we just won't be able to explain.
Nice. And the final question, Erin says she noticed that under the microscope, it almost looked like between late growth sections, there's a
Mm,
lighter section that's not included in the normal growth year. Why is that?
hmm. I'm let me see if I can scroll back up to see what she's referring to. Is it, oh, sorry, this one? I think this is probably what you were talking about. So I think this is the only one yes, that's okay, Erin. I think, Erin, that this is a oak that was sampled. So it is a different kind of tree that I think is called ring porous. And so it's just a different structure of the cells that you were able to see under the microscope. So you would have the early wood section, I think, is here, and this is the late wood section right here. So this forms 1 year growth. It's just different cell structures that are formed in different kinds of trees. Trees that have leaves versus trees that have needles. And you can see that under the microscope, which is really, really nice. It's fun to look at.
Well, that's fantastic. That is all of the questions today. Let's all thank Professor Rayback for just this like wonderful, informative cafe. And I hope to see you all next week for another exciting cafe. So everyone have a good night and go out in the woods and learn about your trees.
Hope to see you out there. Thank you.